is part 3 of my preliminary HSC or Year 11 engineering studies videos on electronics and electricity. This one will be focused more on electronics. Prior to this, I have started with this video where I talk about, they call it that because of the electricity, the Scranton Watt. This is where I keep most of my electricity posts. Things like, let's have a look. We have how we generate electricity, conductivity, electrical circuits, and mostly on how we generate electricity goes in here. Some stuff on AC and DC, a little bit of stuff on rectification is going to come back in a minute, but that's mostly what it is. Okay, one thing I'll quickly mention before we go on is that in this diagram here we can see some resistors and some transistors that we've identified in the previous video. We saw that, well, resistors can look like this and transistors can look like this. They don't have to have a circle around them to help us to spot them. And we can see that diodes don't have to have the circle either. We can tell this is an LED because it has two arrows coming out of it. And in this, what's interesting is this is actually what the wiring for what's called a Nand gate, which we're going to learn about in a second. One thing I didn't cover, which I should have, is that resistors typically look like this. They don't have to, but resistors in electronics, and they have a color code to help you tell how many ohms there is on a resistor. So I just thought that was worth mentioning, that that's a color code that people use. And it's printed on them. We've talked a little bit about diodes, and we've said that diodes will only work on DC circuits, and diodes only allow electricity to flow in one direction. So if you're old enough to know who One Direction is, then yeah, that's a thing. Get out of my head. Okay, so diodes can look different. The different ways that we can have a diode look. The one that we're most familiar with is the light emitting diode, which is an LED. And somewhere on one of these posts, I guess I have it down the bottom here, about how someone got a Nobel Prize for developing the blue LED. Because with a blue LED, you can combine them to make a white LED. The green and red ones came first. Finally, we've talked about rectification. So in order to convert AC to DC, we need a set of DC motors. We saw this guy. We saw him in his video talk about how he converted his AC electrical supply to DC just using a diode and a capacitor. And we said how capacitors store charge. I didn't really want to get this now, but I guess I'll do it. We'll go to calcium is the one most likely to have this. And if we go to more media albums, I have my album on questions on rectification. Do you see? It's Tesla. See, I swapped them because normally they're the other way around, because Tesla, he's all about AC. He's team AC. And Edison, he's team DC. And this band in the background, that's the band AC/DC. And why is Wreck-It Ralph there? Because he wrecks things. He's going to rectify the situation. But okay, so this is the Year 12 book, the notes from the Year 12 book on rectification. And I'll put them all in one spot. And then here's some past HSC questions on rectification. But we also need that as part of like crystal radios, so that comes into our telecommunications questions. I am not going to go through these now, but I might ask in Year 11, I might say, can you identify this device, right? This question here, it says, what is the purpose of this circuit? Inversion. Inversion is the opposite of rectification. Modulation, no, it's not for modulation. Diodes are used in modulating telecommunications, but we haven't done that yet. Transformation is for increasing or decreasing it's for decreasing voltages. And we have rectification. That is the correct answer. Yep. So you should be able to recognize that, and that's a question that I maybe could give you. Okay. rectification, converting AC into DC. So back to our notes. So the thing I wanted to talk about was the resistors, and the resistors have a color chart. And with that, we might come back to these when we talk about our circuits in a second. Okay, so the first thing we really want to learn about is we want to learn about what is a semiconductor and how do we apply them. So we have this video here on transistors. Again, this is a Veritasium video. I like this video. I have a quiz that I have on the video, and what it talks about is it says that in this computer he has 1 billion transistors, right? And that what a transistor is really just a switch.
Controls the flow of electric current. It can be off, so you can call that the 0 state, or it could be on, the 1 state. And this is how all of our information...
I'm not sure if I said this in a recording that I lost, that if you had 3 switches, we'll label them A, B, and C, and you wanted to see if they corresponded with the light globes D, E, and F, if you could only go there once, how could you figure out which switch corresponded to which globe if you weren't allowed to go back and try and make more than one attempt? Yeah, so for example, what we could do is we could turn A on and leave it on for about 10 minutes, and then we could switch A off, and then we could turn C on, and okay, it's easy to identify that which one C corresponds to because it's going to be the one with light coming out of it. But if we wanted to differentiate between A and B, well, we could feel the temperature of an incandescent globe. Now, this wouldn't really apply for LEDs because they don't heat up the same way that incandescent globes do, because they were inefficient. So I just thought that was an interesting thing. So we're going to look at switches in this video. And I just thought that concept of thinking about switches will be useful for us. Okay.
Information is now stored and processed in zeros and ones.
So the idea is, and this is where I want to get to now, is that if we wanted to store a signal, if we wanted to store a code, how many codes could we store with 6 light bulbs? I have 6 light bulbs, and I want to send some secret messages to my secret spy friends. Okay, so the answer is 2 to the power of 6. Let me type that in the calculator. 2 to the power of 6. 64 messages I could put in my code book. Well, so first of all, the first code is if I have them all off. Now, the code might be no message or, stay quiet. That could be my first code, is if I have all off. But beyond that gets a bit confusing. So let's have a look if I just had 3 light switches. 3 light switches, it makes more sense. If I have 3 light switches, well, yeah, let's start off. Actually, I'm going to go back one step. If I have 1 light switch, I can only send 1 message. Now, when I was a kid, there was a TV show called Full House. My kids have seen Fuller House, which is the next generation of Full House. I don't know. It was never really for me, but I did watch a little bit when I was very little, when I was year 1 or 2. And in that show, there was Uncle Jesse. And Uncle Jesse, he was the cool one. And he recorded. He had a recording studio. And he had a light above his door that was red when he wanted to record, so that the kids knew not to come and interrupt him when he was recording. That was the lesson they learned at the end of the episode. He put in the red recording light so that people didn't interrupt him. But imagine if he had a second light. So with 1 red light, he could only have 1 message. Red light on, don't come in. Red light off, I'm not recording. That's it. Well, sorry, he can only send 2 messages. I'm recording or I'm not recording. 1 light gives you 2 messages, yeah? What about if you had a green light? If you had a green light, let's say it's I'm hungry and I want a sandwich, right? Well, in that case, he can send how many messages? He can send I'm not hungry and I don't want a sandwich. I'm not recording and I don't want a sandwich and I'm not hungry. I'm recording and I am hungry. I'm not recording and I'm hungry. And I think I can't remember which one I've left out, but he can have 4 messages. Yeah. No and no, yes and yes, yes and no, no and yes. 4 messages that he can have with 4 lights. Or we could instead, let's say he wanted to say what favorite animal he had. He might have duck is red light. Chicken might be green light. Red and green light might be mongoose. And no lights is his favorite is fish. Yeah. Okay, if he has 3 lights, let's say he has a red, green, and blue light, how many messages can he have now? Well, it's going to double the number of messages. If he could have 4 messages with 2 lights, he's going to have 8 messages with 3 lights, right? He could, and that's what we do. And if we have 6 lights, well, we can have 2 to the power of 6, which is 64. 2, 4, 8, 16, 32, 64. 64 messages, which means we can have we could use this to represent, say, the numbers from 0, no lights, up to 63, because we've got to count 0 as one of those messages. So we only get 63 out of if we're including 0. So under that rule, well, what would this number be? It would be 0 in the ones column, it'd be 2, and then 0 in the fours column, and then 8, and then 0 in the 16, and then yes, there is something in the 32 column. So it would be 32 plus 16 plus 4. Well, 16 plus 4 is 20, plus 32 is 52. This would be the number 52 in that code. And this is how computers store information. They have switches that can either be off or on, and we pair them up in groups of 8. Right? That's just a convention. We use groups of 8. We call every switch that's on or off a bit, and we represent that as a 1 or a 0, and we group them into groups of 8. Okay, with that, I'm going to let this video keep running.
Little bits of electric current. But unlike this switch, a transistor doesn't have any moving parts, and it also doesn't require a human controller. Furthermore, it can be switched on and off much more quickly than I can flick this.
Okay, so the advantage of transistors is that they are tiny, they're incredibly fast, they have no moving parts, and they can be controlled without human input. Okay, so let's have a look at how do these things work. Well, transistors, so before we had transistors, we used to have things called vacuum tubes. That looked like this. And then they developed something called Bell Labs. They developed their first transistor that looked something like this. And it's pretty large compared to a modern transistor. Right? So that was their first transistor. It's smaller than I initially thought, but yeah, that was the first transistor. And then modern transistors, well, we can fit 1 billion of them on something the size that's about 50 millimeters by 50 millimeters in a modern CPU. Okay, so let's keep going on this. So what is it made of? Well, it's made out of silicon. So in the we have a nuclear reactor in Sydney, and what it does a couple of things. It has really, really good X-rays, except instead of being X-rays, they're neutron microscopes. And that's the first thing. They're even better than electron microscopes because neutrons don't have a positive charge. And they make radioactive medicine for people with like chemotherapy. And then they also make silicon, and they dope silicon. So what they can do is,
Which means it conducts electric
if you take a lump of pure silicon,
as well as metals. This is
silicon is a semiconductor which conducts a little bit, but not as well as metals.
because an atom of silicon has 4 electrons in its outermost or valence shell.
Okay, we know about valence shells. Silicon has 4, same as carbon.
This allows it to form bonds with its 4 nearest neighbors. I know that. What's that? So it forms a tetrahedral crystal. And since all
Like diamond.
these electrons are stuck in bonds, few ever get enough energy to escape their bonds and travel through the lattice. So having a small number of mobile charges is what makes silicon a semiconductor. Now this wouldn't be all that useful without a semiconductor's secret weapon, doping. You've probably heard of doping. It's when you inject a foreign substance in order to improve performance. Yeah, it's actually just like that, except on the atomic level. There are 2 types of doping, called N-type and P-type. To make N-type silicon.
Okay, so confusingly, they're adding phosphorus, but phosphorus gives you an N-type, and they're adding boron to get a p-type. And the idea is that boron has either boron has one less electron, which we call a hole, and phosphorus has one extra electron, so it has an excess of electrons. And we can talk about holes moving through the lattice, or we can talk about electrons moving through the lattice. Doesn't really matter which one we use well, it does matter, but for the moment they're both important. Okay, so what happens is we can have a barrier that only works. We can have a barrier that only allows electricity from flow from these ends to these ends when there's a charge applied at what's called the gate to the P's. Now, he's going to go through this in more detail, but for us, what we need to know is that electricity won't work unless there is electricity applied here. If there's no electricity applied here, it won't work. Now, what's interesting is that transistors have got smaller and smaller. We've been able to fit more transistors on each. If we have a chip that's about 50 millimeters by 50 millimeters, we've been able to double the number of transistors on a chip pretty much every 18 months to 2 years for the last 40, 50 years. We call this Moore's law. But we're getting closer and closer to the point where we're going to have quantum tunneling and where we won't be able to get any smaller. So people are looking for solutions so that we can keep our computers getting faster without worrying about quantum effects ruining things. One of those is quantum computers. Okay, so this video I think is pretty good and worth watching in full, but I'm mindful of, it wouldn't make much sense for me to watch a video that you can watch on your own time. Similarly, there's another video that I think is quite good. And I use this video to remind people that transistors, and to show you what transistors look like, can also be used as amplifiers. They have a similar diagram. They show some silicon, and they show regular silicon with having 4 valency electrons, and then they add in doping. They dope, this is N-type doping, so they've added, that's probably phosphorus, and then they can add in P-type doping, so probably boron, but it could be others. So we can add in arsenic or germanium, I think is the other ones. Okay, so what we get is a situation where the electrons can only move.
Electron level of a more basic component, a diode.
Okay.
A diode is formed when
so with a transistor, we'll just quickly go back.
Is born. But if you really want to understand how a transistor works.
Okay, so the transistor will only work when this battery is on. If that battery is not on, the electricity can't flow from the big battery. But before we get to a diode, what's a transistor? What's a diode? Well, a diode is where we just have 2. We just have an N-type and a P-type. And in that situation, they will not allow electricity to move. Those holes, they'll get stuck. So a diode, well, they'll only allow electricity to move in one direction.
If you reverse the power connection, the situation is quite different. Assume that the power source has enough voltage to overcome the potential barrier. You can immediately see that the electrons will be pushed away by the negative terminal. When the electrons cross the potential barrier, they will be drained of energy and will easily occupy the holes in the P region. But due to the attraction of the positive...
So the point is that diodes are a sandwich of 2 semiconductors. A transistor is a sandwich of 3 semiconductors. And a transistor will only work when the electricity is applied.
The power supply should have enough voltage to overcome the potential barrier. So,
if you don't apply electricity here,
electrons will get attracted by the positive terminal of the first.
Electricity won't flow. It will work as a gate. Yeah, and so transistors are tiny microscopic switches that we can control. Now, what do we do with these tiny switches? Well, what we do is with these tiny switches is we make gates. So we're going to go back to Kierkegaard. They've got a video on quantum computers. I'm not interested in the quantum computer part. That's beyond our course. What we want to know is that computers are made up of parts. We have memory, we have arithmetic units, we have control units, we have different parts of the computer do different things. And
Control mechanisms. Computer chips contain modules.
Computer chips contain modules.
Contain logic gates.
And modules are made of gates. So let's have a look at an example of some of these gates.
Which contain transistors.
Gates are made of transistors.
A transistor switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are...
Okay, so if you have 2 bits, you can have 4 colors, right? So a Game Boy, back in the days of the original Game Boy, they could display 4 colors.
are used to represent more complex information.
So 8 bits can represent the ASCII characters,
Several bits are used to represent
which are used in computers.
more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding 2 numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simple.
Okay, so yeah, they go on to say that what a computer does is very simple. It's
In first grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm...
Okay, that's probably good enough for us. So yeah, quantum computing might be a possibility as we go into the future. So we saw in that video, we saw that there was some different gates, and we saw that they were arranged in different combinations of transistors to make these things. Now, the one that's really important is the NAND gate, right? So the NAND gate, your brain is made up of 1 trillion NAND gates. So each synapse connection behaves like a NAND gate, and NAND gates can be used in combination to make all the other gates. So I mean, your brain is not a computer, but that is a concept that we can use to give a comparison of how we can make everything out of NAND gates, which is where if we have a programmable computer chip, we just program everything by rewiring NAND gates. But we do use AND gates, NOR gates. So these are the 4 that you need to know. But in the core, so they're the 4 that you need to know, and they will be given on the formula sheet. So I'll just show you that they are on the formula sheet. That's the formula sheet. But there is also NOT gates. So, I mean, is this so bad it's good? There's effectively, you can just say that.
This is the NOT gate. This is the OR gate. This is the AND gate. And together they are the logic gate squad.
Okay, so you can watch this, and I haven't watched this one in Crash Course, and again, I'm not logged in to check it out later, but Crash Course is usually pretty good. The fact is that we could think of, really what we have is OR gates and AND gates, and then we can have a NOT gate stuck on top of them. A NOT gate stuck on top of them, it just reverses whatever the OR gate would do. It just flips it and reverses it. Can I get your phones down? So this is an app called Circuit Scramble, and just in case you don't have access to this app, I have a different app on my phone, which is also just a whole bunch of logic gate puzzles. And I think this one makes it says the word AND, right, to help you to figure out what's going on. And it just goes through various levels. But if you find, you'll be able to find on your phone, no matter what it is, you'll be able to find apps where you can just do logic gate puzzles as practice. Now, there's explanations of these gates. So this is what I have from the University of Surrey, which talks about truth tables. So the idea is that we can talk about what happens with these different kinds of gates. Maybe I had this open somewhere else. Yeah, I did somewhere here. Okay, it's okay. So we have and, or, and not. The logic gate squad. And they show how each of these can be made, where how a NOT gate can be made from a NAND gate, right? And it doesn't show that for all of them, but... okay, so the idea is that if A is 0, well, AB is going to be 0. That makes sense. Because this gate says, I always like to think of it as like a bouncer. Now, you guys probably aren't old enough to experience bouncers at clubs, but the idea is that sometimes you want to get into a club. You know, in Night of the Roxbury, they want to get into the good night club, and they look at the list. Oh, in New Girl, they look at it, you know, to see if your name's on the list, and the bouncer checks the name on the list and says, "Sorry, you're not on the list. You can't come in." And now this bouncer, the AND gate, both Alice and Bob have to be on the list to get in. If Alice is on the list but Bob isn't, the bouncer says, "Sorry, can't come in." But the OR gate's a bit more generous. As long as Alice is on the list, she can bring Bob in with her and says, "You know what? It's okay." So let's have a look. This is what a truth table looks like. If A is 0 and B is 0, so if Alice is on the list and if Alice is not on the list and Bob is not on the list, no one is on the list. If Bob's on the list, no one's on the list. If only Alice is on the list, no one's on the list. The only way they can get in is if Alice and Bob are both on the list, they get in. Whereas with OR gates, look at that. In 3 out of the 4 scenarios, the bouncer lets them in. If Bob's on the list, you're both in. If Alice is on the list, you're both in. If you're both on the list, you're both in. Yeah, very generous, that bouncer. The NOT gate is like a crazy manager who just, every day it's Bizarro World, and just says, "Hey, you know what that gate was going to say? Yeah, I don't care. Just do the opposite." Right? So if you have a NAND gate, it's just like, just imagine, I always write the answer for the AND gate in the middle, and then on the outside, I just reverse it. So in this case, neither of you on the list, you're both in. Oh, Alice is Bob's on the list, but Alice isn't. It's okay, you can come in, right? Don't worry about what that bouncer says. If Alice is on the list and Bob isn't, don't worry, you're both in. I'm changing changing the bouncer's mind. You're both on the list. Bizarro manager says, "Sorry, you can't come in," right? The NOT dot. It's just crazy. I always like to think of it as being like Missy Elliott, where Missy Elliott flips it and reverses it. I should have had this song ready to go. I have no idea what she's saying after that, but yeah, put your thing down, flip it and reverse. Okay, so hopefully that's not a rude thing, I don't know. So a NOR gate is like an OR gate, but just the opposite. Now then there's this thing called the XOR gate. Now generally just written as XOR. XOR gates, they just say, okay, I'll let you in, but only if one person's on the gate. If Alice is on the list, you're in. If Bob is on the list, you're in. If you're both on the list, bomb, shut it down. If neither of you are on the list, shut it down. The XOR gate, it's crazy. It's a crazy gate. But the XOR gate is really useful because we need XOR gates to do addition. Yeah. Okay, so let's have a look at a visual representation. Okay, so we've seen that it's in the book. We've seen this. Okay. We'll come back to that. Okay, so we've got this representation of gates using water, right? An AND gate using water says, no, you need to both be on the list to go into the pipe. Or, you're in. As long as there's water, you're in. An XOR gate only works when it's, see, if they're both on, switches it off. Yeah, I just think it's a great video. So just a representation of those gates. Now, you can't really show an NOR gate. Well, I mean, I'm sure someone could come up with something. Okay, so how do computers use these ones and zeros? How do they do things? Well, like we said before, they convert all those switches as being in binary. Binary means it's either on or off. Now, writing on or off is a bit, we don't want to write 3 letters for off all the time, and we can't just use the initials because they're both O. So instead we use 0 for off and 1 for on. And you might be familiar with this robot rap.
Solo.
0 0 0 0 0 0 1 0 0 0 0 0 0 1 1 0 0 0 0 0 0 1 1 1 0 0 0 0 0 0 1 1 0 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0
Come on, Sacro Lake, my battery.
Flight of Conchords, great TV show. It's a great episode. Definitely worth checking out the whole thing.
The humans are dead.
Once again without emotion,
The humans are dead.
I thought they had the second half of that song as well. But anyway. Okay, so computers, everything is written as a 1 or a 0. We're okay with that concept. So,
And while almost everybody knows that this is somehow related to what computers do, very few of us seem to understand what binary is or why computers use it. If you want to know, then this video is for you, because let's talk about what binary...
okay, so we want to represent things... If we just want to represent apples, right?
Something higher as that each symbol
We can just show... We can just write down one apple for every amount of
to
things.
represent something higher than 9, we add a digit to the left, roll its first digit back to 0, and start over. This system is very efficient compared to tally marks because each digit we add exponentially increases the amount of things we can represent. Because in this system we add a new digit every 10 things, each digit represents an increasing power of 10. This is the number of ones we have, the number of tens, the number of hundreds, the number of thousands, and so on. Now this is probably something you already know, but it's very important to keep it in mind when we talk about binary. Now binary works the exact same way as based and positional, but instead of each digit going from 0 to 9, it goes from 0 to 1. Counting upwards in binary sounds like this: 0, 1, 10, 11, 100, 101, 110, 111, and 1000. Because each digit of binary has only 2 values and not 10, each additional digit represents an increasing power of 2 rather than an increasing power of 10. So this is the number of ones we have, the number of 2s, 4s, 8s, 16s, 32s, 64s, 128s, and so on. Not nearly as efficient as base 10, but exponentially more efficient than tally marks. Literally. So now that we know how binary works, let's talk about computers. Why did the first computer creators, as wise and intelligent as they are, waste their time with such an ineffective system of counting? Well, it's because of a physical limitation on how computers work. Everything a computer does comes down to what's known as microtransistors. Simple, tiny, eensy-beensy little switches that can either be on or off and can be flipped on or off with a very weak electrical charge. The first goal is to get computers to count. And to get them to count by using these switches, we could use the tally system, meaning the number of on switches equals the number of things we have, or we could use the much more efficient system of binary, where each switch represents a digit of binary. 8 transistors using the tally system could represent a number as large as 8 by turning all of them on. With binary, we can represent a number as high as 255. An on switch means a 1, and an off switch means a 0. Now is a good time to mention that a single transistor is what's known as a bit, which stands for binary digit. A byte is 8 of these bits in a row, which means any number between 0 and 255. So if binary is just a system of counting, what do people mean when they explain how to spell things in binary? Well, what they really mean is how to spell things with ASCII. The American Standard Code for Information Interchange is a way to convert a computer's data, which can only be in numbers, and turn it into letters for humans to have an easier time to work with. ASCII simply assigns a character to each value represented by a byte of binary. And because a byte has 8 digits of binary to work with, and 8 digits of binary can represent up to 255 values, ASCII had 255 letters and symbols to choose from, more than enough for the entire alphabet, punctuation marks, and other symbols. For example, the corresponding ASCII number for an uppercase A is 65. Now 65 in base 10 is equal to 1,000,001 in binary. So whenever you type in an uppercase A in a word program, a coding program, or a scripting program or whatever, somewhere there's a little tiny row of 8 transistors arranged in the pattern of off, on, off, 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 on, which represents 0, 1, 0, 0, 0, 0, 0, 1 in binary, which is interpreted as 65. And
Okay, so
this was a 5.
So, okay, the problem then was that you couldn't really count to numbers bigger than 256, so then they added double bits, right? The ability to have a double bit. So instead of having 8-bit, we now had 16-bit. Now I'm pretty sure that the first SNES, it could only use 8 bits, and then the Super Nintendo, it could go 16 bits, and then computers, right? So like Windows computers, they use 32 bits, and then we had the Nintendo 64, which when it needed to could use up to 64 bits to store information, and then these days modern computers, they now also they have some that works on 32-bit and some that works on 64-bit. And yeah.
You hear people talking about the difference between 8-bit and 16-bit. This is more or less it. But that doesn't mean that a 16-bit system is exponentially that much more powerful, because your program isn't always going to be utilizing all of these numbers in each byte that it represents.
In another video, he then goes to talk about how colors are represented in 3 bytes. So they're represented in 24-bit. So we can, when we talk about colors, we give them something like a hex code. So if I talk about famous colors, so like Ferrari red, it'll give me a hex code. Oh, there we go. There's the hex code, which is another way of writing binary. Or we can write it in the RGB, which is 212 in this out of 255 there, and then 0 and 0. If we have another color like Tiffany blue, that's spelled with a Y. Okay, so they have a hex code as well, which is 81D8DO or 404. Oh, sorry, no, we want the RGB. 129, 129 in the first chunk of 8. And then 216, and then 208. What's also really interesting is that there are illegal colors. Okay, so illegal Numberphile does a good video on this, but I'll show you something like this. I wanted videos is what I wanted, where you can have illegal numbers. Where you could have, there are some codes that are used for things, for decrypting things. So an example of where we have illegal numbers is decoding PlayStation games. They're all encoded with a key, which that key, you're not allowed to share that key. That's an illegal code to provide to people. And so the internet, they, being the kind of people they are, they came up with, they converted the code and they converted it into 28 bits, and they then used the 28-bit to produce colors. And where it was more than, it wouldn't hold in 28-bit, they just had it multiple times. And this video goes through the process and says if you just had a fancy number, this might be that code represented as an image. And then the leftovers you just write down here. So this could be an example. So these are some illegal numbers, which ironically, by making them illegal, they now have Wikipedia pages which display them, and somewhat ironically. But that is the idea when we're talking about illegal codes. Okay, so we're done with that. We're on that one at the moment. We're getting close. So, okay, for monitors, how monitors work? Well, look, that's not really the focus of this course, so I'm going to keep that away for the moment. What I will say is that's the next video, and I'll give you the link if you want to watch that one. But you can count to really big numbers on 2 hands. So I'm not going to watch this guy count on his fingers up to 1,000, but you can see how he can represent using binary. (31) on one hand. So in 2 hands, you can count 2 to the power of 10, which is 1024. Anyway, so if you're not quite sure of how binary works, this video will help explain things. Okay, getting to interesting stuff. I do have one more reply. Okay, so this mechanical binary counter. So this is going to count in binary. Just whenever you turn the crank, it adds 1 to the number. I think that's pretty cool. Okay, so we now know how we can count in binary. Now the next part is how to add in binary. Now I'm going to flick through this to a pretty extreme example. Okay, so we've got some logic gate exercises. These are harder than the ones from the HSC that I posted. Well, they're different to the ones that we would use. They use NOT gates and things like that, which we wouldn't use in the HSC. Or we shouldn't be using in the HSC. They're not in the formula sheet. I have this thing here which talks about the efficiency of LEDs because LEDs are made out of diodes. Okay, so in this arrangement, what we can see is that this is a transistor. It's an NPN transistor. It has 3, and this is the one that controls. This here is what controls. We can see resistors, and that's how we wire an AND gate. I just chose an AND gate, but I think in this series he talks about all of them. Does he have a more traditional wiring diagram? No. And then you can see he's actually wiring it. Now, my understanding is I'm not an expert in electronics and certainly not advanced electronics, but my understanding is that when the gates that we use in computers, obviously they're not wired like this. What they do instead is they can wire everything out of NAND gates. And by just reallocating NAND gates, we get the same effect. Okay, I know where I have in here. This is the wiring for a NAND gate. That's what it looks like. This is how you can wire a NAND gate. And that's why I had that one open. Okay, so transistors, we have how to make an AND gate. In this here, it talks about the efficiency of an LED versus... it's not entirely fair, this comparison. It definitely is fair to say that LEDs are more efficient than... does this not work? Huh. Maybe the host image has disappeared. There you go. So this must be in some sort of museum that shows that if you turn the dynamo compared to the fluorescent light, the thing with fluorescent lights is fluorescent lights take a lot of energy to start, but look at how bright that LED is compared. So fluorescent lights, almost all of the energy is in getting that initial start. Yeah, okay. But way more, about, I think we said they're more than 10 times more efficient. Okay, so now we're going to talk about, this guy's talking about the XOR gates and the half adder. Now, this is probably a good detailed explanation. Computer file is usually pretty good. But what I like instead is a guy who's often on computer file and number file is Matt. He's on number file rather than computer file in this particular video. I think he also does stuff on number file as well. And he's going to show how you can make an adder made out of dominoes. So you can simulate an XOR gate or and an AND gate together to add numbers using dominoes. And what he went on to do is he went on to add, he could add a number up to 8, a 4-digit number in binary, which we said is 2 to the power of 4 2, 4, 6, 8. Sorry, 2, 4, no, 16. So I think he got to a 4-digit number. I think it adds to a 4-digit number. So he adds two numbers that are less than 4 is what he adds. And so he took 10,000 dominoes and he lined up the wiring of his half adder with dominoes, and that's interesting. That's exciting. And this is the circuit diagram, but you need to know what the gate looks like, how to wire the gate inside. So we've seen how we wire gates. This is how we could wire a half adder circuit, and we can see what does that even look like. Oh, here we have an integrated circuit. So integrated circuits are pretty important. Often we don't want to wire things out of individual transistors and wires and things all the time when resistors. What we want to do is we just want to buy something that's just going to do the thing we want, and that's called an integrated circuit. It's covered in plastic, and inside this one you can see just has these logic gates, and that's just what it does. And we have, so this one just does and this one just does ORs. It just does exclusively ORs. And so you can use these two here. It actually gives you multiple of them. It gives you as many, it gives you, in this case, 4 in each. But you can buy an integrated circuit that just gives you AND gates or just gives you OR gates. And you can see that they've done that rather than having to wire their own AND gate and exclusive OR gates. They've used an integrated circuit. I have missed the best part of the dominoes falling, but anyway. You can watch the video, and very exciting watching dominoes. Now, you might say, well, look, I don't want to spend 3 days setting up a domino computer. What you might instead want to do is you might want to spend your time making a Minecraft computer. And this link here will tell you, see, suddenly we're excited. This here will tell you how to wire your own Minecraft computer. And it will tell you how to set up, how to add small numbers using redstone and things. So I just thought that was interesting. Okay, so we've talked about integrated circuits. So if we go back here, so this is what a transistor looks like in terms of its wiring, and this is what a transistor looks like in terms of symbols and what they actually look like in practice if you want to go and pick up one and buy one. There's different kinds. This is how we wire an AND gate. This is a OR gate. So in this case, if A and B, they both need to be close to turn on the light. Yeah. This one is an OR gate, right? If you close A, it's just going to run through. Now this one here, because electricity goes through the path of the least resistance, if it can go through the middle, it will. Yeah. So if we close both, the light turns on. Does that make sense? So both need to be active, which makes it an AND, but it's the opposite of what we expect, which makes it a NAND. And this one here is a NOR gate. The reason I have that is because in 2018 there was a question that asked you to identify which one is the NAND gate. So the answer would be this one. I thought that was a bit of a tough question, so that's why I respond a lot to HSC questions. Okay, we've talked a little bit about integrated circuits, and I'm not going to go into this video. I will let you watch this video in your own time. Crash Course did a good thing on integrated circuits. We've seen what integrated circuits look like, and we can see that they have their own circuit diagrams. And the idea is it's just a lot cheap. It's a lot cheaper and it's a lot more. They're also called ICs.
Semiconducting material, performing the same function as a larger circuit made from discrete components. An IC is a collection of electronic components.
So this IC just has 4 NAND gates. Yep. Okay, and then here's a crash course on NAND gates. I'm not going to, on ICs. I'm not going to go through that. This is an IC, and it has some stuff. I don't know what it does. It's a timer. There we go. A 555 timer. Copeland talks about that in his book. Okay, so we go back to... We're ready? Almost ready to go back to the book. We have a video here on transistors. That's the real engineering. We saw him when we did the materials, that guy. And he talks about how transistors are probably the most important invention of the 20th century. We talk about how do we store information with transistors. That's another crash course video. We have what is a half adder. We just saw the video there on computer file. And we have, what is a Zener diode? A Zener diode is a diode that only operates at high voltages. I have that there because there have been questions on Zener diodes, and I just want to be able to say that we have talked about Zener diodes, and this video here that you can watch later discusses that in more detail. I also happen to have Britney Spears talking about semiconductor physics. I don't know why someone made this webpage. This was probably in the early days of Britney Spears' fame. It's actually very advanced. It's much too advanced for this course. Even the introduction, I sort of start to no longer be able to follow it at about here. So if you are really interested in Britney Spears or university level semiconductor physics, hey, this is a page that you can check out. And with that, we'll just quickly go back to Copeland's book, and we'll say that, okay, we've learned about dry cells, we've learned about rechargeable cells. So we talked about how in the Real Engineering or Wendover, they talked about how the future of engineering could be liquid metals, but we've developed from lithium ion to nickel cadmium, and we've talked about ICs or integrated circuits, and we've talked about what they can do. Examples are pickaxe ICs that can run very simple things, and they can be reprogrammed, and that's very interesting. Oh, so here we have the timer, a 555 IC. That was the one I showed you the picture of earlier. And when we get to more advanced reprogrammable ICs, what we tend to call those is microcontrollers. And so down the bottom, I think I have something on Arduino microcontrollers. We have Arduino microcontrollers. If you want to borrow some and you want to play around with them, I think they're a great opportunity. So a lot of you will have already used Arduinos in junior technology, and we've also used microbit microcontrollers, which are a similar thing, but they're more streamlined. These are just totally reprogrammable. So we have a silicon chip here with a whole bunch of Nand gates, and we can use them, we can wire them into any configuration, and within the limits of its memory, we can program it to do any number of things. Okay, so with that, we're probably done, and I just want to quickly check with, I did want that one because that's not already in my notes. We've talked about microcontrollers. In this course, it says we should know and, or, NAND, NOR, NOT, and XOR. Technically, on the exam sheet, they don't have NOT and XOR, but the fact that Copeland mentions it, I think makes it worthwhile. We have the truth tables. I'm going to turn this guy off so he's not talking over me. We've talked about truth tables. We know how to read a truth table now, and this is an example of the pickaxe, a 74 something IC series, and it's just 4 NAND gates. That's all. When you buy it, you're just getting 4 NAND gates, and it saves you having to wire a whole bunch of NAND gates. And with that, we are finished Year 11 electronics. If you're interested in more, I do have a audio recording where I go into Year 12 electronics up until telecommunications.